H2O, dihydrogen monoxide.
H2O.
Wait, so we use the air molecule.
Have y'all watched SpongeBob?
No.
Where's the monkey going?
I don't know why I won't focus.
Why? Why do you need a monkey?
Yeah, bro, split the piece.
Have you seen SpongeBob?
Oh.
Hey, I'll buy some of them.
Elliot, have you seen SpongeBob?
Oh,
Have you seen SpongeBob?
Okay.
Have you seen SpongeBob?
I did.
Okay. So, imagine this. You have a light bulb or something inside the water. Okay? This is like a point source. It could be light reflecting off of it. Something is either reflecting or emitting this light. So, here's the story. So, when it hits that interface from water into air, instead of going straight, what's it going to do?
Bend up.
Bend up
Speed up.
or bend down?
Bend
Bend
up.
up. Down. We're going into air.
So the light's going from water
Horizontal.
into air.
It's gonna go up. It's gonna speed
So
up.
this is going to come along like this. The top of it's going to do what?
Go flat.
This side up there is going to speed up, right?
Yeah.
It's gonna go up.
So this side is going to go faster.
Bend up.
Go bend flat.
It's flat.
Flat.
Yeah. The bottom one bends flat.
You make
It bends
top
up, right?
one is
Why are two
They both go up.
Hold on.
No, it goes.
So
Wouldn't
this
it?
is the path. You're in water. Okay? You're going into air. What's it going to do?
Bend.
Speed up, right? So imagine this is the axle of the car.
Okay.
This is thick mud.
Yes, sir.
This is dry pavement, right? So as this comes up, this is going to hit the dry pavement first.
Oh no.
This is going to hit the dry pavement first. So what's it going to do?
The bottom
That's
one's
usually Venus' birthday.
Slow down or speed up?
Speed up.
Speed up.
This is going to speed up.
Why are you trying to play it off and look the other way?
What did I do?
Oh, I was telling you. Mike.
No, Nathan's in my
So as that speeds up, which direction is it going to bend?
Go down.
Down. So it's going to bend down.
I
You
trust
that first.
I trust you.
You just come up the top one and say
Like
Oh.
Yes. Just wait for me.
That's insane, Jerry.
this, right?
Yes.
What's the top line going to do?
That's what I meant.
That's going to get it up like this, right? Now, your eyeball is here. What's your eye going to try to do?
Trace it back.
Your eye's going to try and trace it back
Oh my bro.
Oh, it's not like a laser
to
pointer,
here.
It's like a light bulb.
No frickin' way.
So your eye tries to trace it to this point. So what are you going to think? Is it further out or actually is it closer?
Closer.
It's going to appear closer.
Nearsighted. We should have done
Okay.
it before. Nearsighted.
Well, no, this will make sense
Oh
now.
yeah, nearsighted.
So, let me explain this in just a second. This will make sense in just a second. So your SI,
What's the homework situation looking like?
They'll probably tell us at the end of the lesson.
No, maybe we waited and we're a little patient about it.
He starts smiling, that's what he
I
means.
just need to know.
Why are you smiling? Brother.
Why do you
Stop
think
smiling.
Oh, this is the one and only.
No, we have half the site.
It'll take you literally 10 minutes. Okay, well, we gotta restart.
Okay. So, there's two different ways you can see this formula. One is it's N2 over N1 times S naught. S naught is like the original distance. That's like in this situation, that would be 10 centimeters. That's like the actual distance, how far it is. This is like the image distance, like where it's going to appear. So in this situation, it starts with an index of refraction of water, which is 1.33, and it finishes in air, which has a value of 1. So if you go in or in not, N2 over N1, it's the same thing. It's however you want to put it. I'll have this equation for you on the test. Don't memorize it. You just have to know how to use it. So in this situation, it finishes with an index of refraction of 1. It starts at 1.33, and then I'm going to multiply that by 10 centimeters. So right away, what do you know about the distance? Just mathematically,
Small.
it has to be less than
10.
10. Okay? So if you do the math on this one, you get like 7.5.
Yes, sir.
Okay? So what that means is if you're on the outside looking in, it's going to look like it's 7.5 centimeters in front of you. But in reality, it's 10 centimeters. So this is you looking in. Okay? You're looking at the fish. So the fish are going to look closer than they actually are. Okay? Go with that. Now, the opposite of that. We're going to have air out here, same situation. Then we're going to have water. And then we're going to have this point source out here.
Hey, Shaq, stop playing with the train.
It's normal as they get.
Hey, Nathan.
Okay? All right. Now, this one, you're the fish
Slow down.
looking out.
What?
So when this light goes from the source, from the air into the water, what's it going to do?
Slow down.
Flat.
Slow down. So this line gets
Flat.
flattened out. Okay? This line gets flattened out. Now, if I reverse those back,
Far away.
what are you going to think?
Far away.
You're going to think that it's further away because your eye tries to reconstruct it based upon the path that you see it take. Right? Now, so it's going to be the same thing here. The only difference is that now I'm starting in water, okay, or I'm starting in air and it's ending up in water. So now that's going to be 1.33 over 1 times 10, and you're going to get,
13.5.
okay, whatever that is. So in that situation, you're going to think it's further away than what it actually is. Okay? Good with that. So if you're going from more optically dense, or from less optically dense to a more optically dense, it appears closer. If you're going from more optically dense to less optically dense, it appears further away. Okay? So basically it's like acting like a lens. Okay? All right. So I need somebody with the calculator to make sure that you're in degree mode. Okay? Air, water, okay. So this should be old school. Okay?
Stop playing with Thomas the Train.
We didn't want to let it get in the hands of Gavin. So
Yo, why you playing with
Yeah, I might leave it.
Why
Sorry.
you said
Why
it's
you
twice
hands
the
up,
same
Gavin?
thing, man.
Just to be fair. You said
This should be old school. I have a beam of light going from air into water. Angle is 40 degrees. Index of refraction of air is 1. Water is 1.33. What should that angle be?
Less than 40.
Less than 40, right? So we can take 1 times the sine of 40, and we can get 1.33 times the sine of theta. So somebody take 1 and divide it by 1 times the sine of 40. Or we don't need to do that. Take the sine of 40 divided by 1.33 and then take the inverse of that. 28.9 degrees. Cool. Okay? So 28.9 degrees. Remember that's measured from the vertical. Slows down old school. That should be absolute old school calculation. Should not be a problem.
literally.
Now, we're going to reverse it. So now I'm going to have the air up here. I'm going to have this angle. I'm going to have the beam of light going from the water at 40 degrees into the air. So what's it going to do is that as it crosses that interface from water into air,
Speed up.
speed up. So since it speeds up, what's it going to do? Flatten out, get steeper.
Steeper.
Steeper. Why?
Cheaper.
It's better.
So this is coming out like this.
Right.
This, the top of the wheel speeds up
Right.
because this is dry pavement. That's going to go faster.
Right.
So it's going to flatten out,
No.
or it goes steeper.
Flat.
Let's just do the math. Okay?
We're in this here.
Math is flat.
So
Flat.
I'm going to take 1.33 times the sine of 40 divided by 1. And what do you get for that angle? 58.7?
Uh-oh.
Right.
How did you do that in your head?
So that turned into 58.7 degrees. So what did it do?
Flat.
Flattened out. Okay? Flattened out. Because the top side sped up and it flattened out. Cool. Now, we're going to shift it. That was at 40. So now I want to do the same thing. Water, air, but now we're going to make that 50 degrees. So somebody take 1.33 times the sine of 40, no, of 50, I'm sorry, 50, divided by 1, and find me that angle. What do you get?
Don't expect the answer to be anytime soon.
Guys,
73.
guys,
So just put it in
I
the
switched to
calculator.
remote.
I don't have my
Okay, give me a second.
Give me
You
some.
get an error message.
Yeah, because you can't do that.
You can't do that. You can't do that.
Why not?
It's undefined.
You can't even do that. You
Okay?
can't do what?
It becomes undefined.
Oh, wait.
Wait, what?
Hold on. So basically, this is this whole idea of internal reflection. Okay? So,
Oh, you said there was an angle.
there's a critical angle. Okay? So at 40 degrees, that flattened out to 58.7.
Oh.
So if I go up to like 42 degrees, what's going to happen? Going to flatten out even more. At some point, what's it going to do?
180 straight on.
Horizontal.
And that would be 90 degrees. So at 90 degrees, it would run parallel with that surface. Now if you try and take the sine of like 91 degrees, doesn't make any sense. So what happens after that, then it bounces back in and you have total internal reflection.
I'm not doing what is.
No, you don't have to worry about it going from air into water. Air into water won't happen. Because of the fact that it's slowing down. The only thing that's happening is that you're making it then closer to the vertical. But if you're going from air or water into air, then there is a point where that reflects back. Okay, so here's the map.
What's that?
That's called the critical angle. So, to find the critical angle, it's in over in naught. So in this situation, that would be where I end up would be 1 divided by 1.33, and then the inverse sine of that. What do you get?
48.75.
48.8 degrees. So if my angle is less than 48.8 degrees, it'll flatten that out. If I'm at 48.8 degrees, it's going to go parallel with it. If I'm more than 48.8
It goes
degrees,
down.
then you get total internal reflection. Okay? Now, if you reverse it, somebody try and do this with 1.33 over 1.
Let me guess, it doesn't work.
It doesn't work.
No.
That's
That's
above
zero.
Mr. Burkett, you showed us that with that.
Oh, it's like.
Well, it's almost like I knew where we were going to end up.
Whoa!
Why it's just like,
Yo, all the physics connects, bro. Isn't that insane? Bro, the prophecy's true, bro.
okay, that was
Think he knows
funny,
what the next
Wyatt.
unit is?
Okay, so this is how you can tell. So look what happens. This only works when you're going from a more optically dense medium to a less optically dense medium. Okay? All right.
I think David's part of that. Mr. Burkett.
No, it's not.
Okay.
This is
Stop
not
it.
No, it's not.
Yeah, Mr. Burkett.